Welcome, everyone. So today I am here joined by James Douma and Scott Walter. James is a very knowledgeable person in the field of AI. Most of the people here in the Tesla community are very familiar with him from his interviews with Dave Lee and other people. And then Scott Walter has been very deeply involved in industrial robotics for the length of his career. Created a company that actually makes simulation software that allows companies who are going to be setting up a factory to get an idea of exactly how all the industrial robots that they need are going to interact with one another and streamline and make all the mistakes that they're going to make in setting up their line, or at least the first pass of those mistakes in software, instead of having to invest a bunch of money to not only purchase the robots, but get them all installed where they need to go. And then find out, oh, we need to move this here, we need to move that there. And so these are experts in the field of manufacturing and AI. And today we're going to be exploring the question of how are humans, Optimus bots, and industrial robots going to collaborate in the future as Tesla continues to develop the world's best robotic brains. And currently there's an entire scheme that works in, but I think that as artificial intelligence seems to be changing a lot of previous assumptions and the way that the world has worked in the past, we're going to be thinking about how it's going to do that here in the localized context of the manufacturing process. And as Elon says, the factory is the product. And so just curious to see how that is going to evolve in the context of Tesla and what that's going to mean for the company overall. So yeah, great. Thanks for joining me today. And Scott, would you like to kick us off?
Yeah, so thanks for inviting me, Hans. And James, again, it's good to see you. It's always a pleasure to have these discussions. And notice we're focusing on like one question today, because between James and I think one question will take 5 hours to answer. So, okay, we're going to try our best. And what can you do to get from the current state of the art in the factory? And if you've ever been in an automotive factory, they are amazing. I mean, every time I walk them, I cannot believe that the human mind could actually come up with these things and they're all working together. And despite that, they're still terribly inefficient. There's a lot of room to improve, lots and lots of room. And that's something that Elon has seen. And he wants to take it to the next stage. And this is his idea of this alien dreadnought, where like everything is compacted down to as most efficient space as possible. A lot of reasons for that. One is that there's so much stuff going on, trying to optimize it is just extremely difficult. There's just too many variables. And you can imagine just AI alone might help you in the planning phase to figure out what's the best way to set everything up. And that most everything right now is done by rules of thumb. So you go back to Henry Ford, somewhere along the way, he came along with the idea of the production line, and that the stops were going to be like around a minute long. So they just kind of decided over 100 years ago that 50 seconds is about what you've got. And they're sort of stuck to that. And no one has really gone down there. It's like, well, is that really the optimal one? Or is that the optimal one for this particular model? Can we do something else? And it's because there's just too many variables. At some point, you just have to say, put a line in the sand, like, this is it. Everyone has to design around this and just do the best effort you can. And what I see is like the alien dreadnought is as much as the automotive factory is impressive, Elon has pointed out that only 3% of the volume is actually doing anything. You get a lot of this empty space all over the place. You have aisleways everywhere where nothing is going on. It's just so you can transport. Basically, it's your blood vessels to be able to move everything around. So you look at it and say, we must be able to make it more and more compact. Now, if you've ever opened up like a copy machine and look at that, I mean, that is absolutely the tour de force of what it's like to like make everything as condensed as possible to be able to mass produce copies of something. So just imagine that's what you want to do. You want to take the entire factory and somehow compress it down that it almost looks like a copier. And the reason why copiers work the way they do, unlike a printing press, or let's say a line we're publishing, is like there's no humans involved. It's completely automated. You know, if you go to a factory that is doing printing or something, there's people around there. You've got to accommodate for people. You've got to have services people. You've got to give air for them to breathe. You've got to give them space and everything else. So you start taking the people out, and maybe now you can start to compress things down a little bit. And perhaps to give an idea of what we're talking about, I think you've queued up a video of the spot welding lines that they have at Giga Berlin, which will look pretty impressive and pretty compact. but then look at it and say, is there room for improvement here? What can we do?
I am pulling that up now.
Okay, so everyone knows that it's the fly through. Look at what the robots are doing. They're trying to do assembly, count the number of robots that might be in an individual cell, see what's going on. It does move pretty quick, so sometimes you have to pause it to see what's going on. So we've got robots that may be putting some body panels in place and then spot welding them together to then move to the next station where more welds will be applied and more welds and more welds. And they all have about 50 seconds to accomplish whatever it is they need to do in that cell before they progress to the next one, the next one, the next one. So right now, I think the frame is frozen. I don't know if you're seeing it on your side. Okay, here we go. And so we come in here and we can see more of these robots kind of moving around. You can see there's some above, there's some below. So in some cases, you might have 4 robots in the cell. Other cases, you might have 6 or 8. You're trying to get as many in there, but you can still see there's a lot of free space around there where nothing is going on, but it's still quite impressive. Yet if you look at all those cells, you'd say, well, wait a minute, it seems like they're repetitive. Can't you just accomplish that all in one? And the answer is that, well, I suppose you could if you had enough time, or you could compress them together that you could do a little bit more. But in many cases, your end arm tooling isn't the right size to be able to get into where it needs to be. But still, think about that. That is pretty compressed, but you can still get in there. And right now, the state of the art might be you can get close to a dozen robots in there. Toyota is trying to press that to get 24, at least 24 or more in there. And to do that, they have to completely redesign the arms to allow the accessibility, because it really is too many cooks in the kitchen, if you think about it. They're all getting each other's way. How do you coordinate that? How do you make sure they don't get in each other's way? It's a very complex problem. In many cases, you just have to take shortcuts and just say, you know what, the problem will be a lot easier if we just subdivide it rather than trying to accomplish everything in one very, very tight space. Doesn't mean it can't be done. It just means it's a very complex problem. And James, I can see you're kind of biting at the bit, probably waiting to go. So.
No, I'm good. I like listening to you talk about this stuff.
Okay.
It's funny. So listening to the stream of stuff you were just talking about, I'm thinking about the tension between optimization, getting something really dialed down, like the copier machine, or, when I think of the alien dreadnought, I think of like, if you've ever cracked up one of those old mechanical calculators and it's just like wall to wall gears, just chockless, like no space, or like a mechanical watch, you open that thing up and the guys have really optimized everything down. Now, of course, if you want to make a change to a mechanical watch, or if you want to make a change in one of those calculators, like once you've got it built, your optimization is kind of working against you at that point, right? Because the more tightly you pack stuff together, the more the ripple effects of making any one change do, right? And when you look at factories today, like flying to that gigafactory, like most of what you see is empty space, like all that space up to the ceiling, like there's nothing there. So the idea of like making best possible use and filling all that with machinery, like that's cool. That's a kind of optimization, right? But it's, like it's going to work against you to some extent if you have a dynamic environment. Like we want to be able to make changes on the fly to the cars, or we want people to be able to go in and debug, or we want to be able to modify one line, shut it down, operate everything on a second line, or move everything to the left so we can introduce like a lot of that stuff you lose when you. So one of the reasons factories are so freaking big is because people are just like, oh, we think it takes this much space. Let's just build a giant building and we'll figure it out as we go. It gives you a lot of flexibility because you've got all this space to move stuff around. But yeah, it costs money. So once AI starts coming into it, the thing AI gets you is it gets you generality. Like the machines themselves become much more on the fly kind of stuff, and maybe even adaptable. Like right now, human beings aren't working on assembly lines. They're pretty general. You show them approximately what to do and they may mimic that. But as they get better at the job, they constantly refine, and they can on the fly ad lib. Oh, we're out of this part. I'll work on that for a couple of minutes. And then when the bin comes over, then you catch up. Like they can constantly rearrange the order that they're doing stuff in because they're general, right? So in a sense, one of the things that AI gets you is it gets you like all the robots start to be able to do that, right? You like on some level, you get to do your optimization on the fly. you can imagine at some end, you've got this really arbitrary alien dreadnought and like, oh, today we're going to make iPhones and tomorrow we're going to make calculators. And, so that it's completely dynamic. So I think these two things are kind of in tension, right? Like you can get super, super optimized at building one thing that you've thought through and you've spent a lot of time on it and you've really tuned it up. But then you lose flexibility. So, the other kind of optimal thing is like the anything factory, right? Where like you can do anything with it. It can reconfigure on the fly. It's super dynamic. It can make several products, alternately as it goes. You can change the feedstocks and it can adapt. And so that's another kind of vision of optimization.
Yeah. And that's where the term flexible automation comes in, because you have the hard automation where you really are making one product, but you're making it really well and you're making it really fast. So, the classic example is a bottling factory. I mean, it's hard automation and it does that and it's just kicking them out in the millions. The automotive factory, because your volumes aren't that high, you need to have a little bit of flexibility to be able to program it. And many reasons that the robots are used the way they are, it's not because they're so much programmable, but they're flexible. Oh, I can use the same piece of equipment to do this thing and that thing and that thing and that thing. So they're really using it that way. But the irony is that the whole idea of the robots is like, oh, they're flexible. We can reprogram them real easily. And it's like, well, maybe we can reprogram them, but sometimes it's not as easy as you think it would be. So a lot of time is spent in getting the robots to be programmed together. And then as they start working closely together, you have to start coordinating that stuff. And it gets really tough. And then you've got to make sure that everyone accomplishes their task in a set amount of time. And if not, people are sweating bullets out there trying to figure out what I do to make that move a little bit faster. And then they suddenly say, I can't hit all the welds. Can some other station take up this weld right now? So you might move those things around. And then getting the density in there. Again, the robots themselves, because the way they're designed as a 6-axis arm, because that's the minimum number of joints that you need to be able to reach all positions and orientation in space. That doesn't mean you can't have more. And the reason when you put more in there is now you get redundancy that your elbow, rather than always having to be in one position, you can start moving around a little bit. So they want to come up with these robot arms that have a little bit more of that flexibility so they can really work next to each other. And I had seen one of those videos that, Toyota is working on these arms that start to look more like a snake than a traditional robot arm, because they might have like a double elbow. And rather than orthogonal joints, they kind of are at 60 degrees to each other, the way they roll around. And when they put them all together, if you look at it a little bit blurry, you'd think you're looking at like a dirt pile with earthworms in there. They're just kind of like moving around all of a sudden. And it's just all of a sudden you get this chill down your spine. That's the alien dreadnought. I mean, it's gonna be one of those things you're gonna go in, it's really gonna look like something out of Alien, that you're gonna be freaked out by what you're seeing, because now the mechanisms are really honed. And it's that balance between how do we make sure it can be flexible enough to do something different. And literally, I mean, they have to be flexible to be able to get in. It's not just a question of can they reach the point, but can they access the point? So a lot of times, like, yep, it's all in the robot workspace. Okay, can you get there? Oh, no, we can't. The part's too big, or this is in the way, and the fixture, and you have to change everything. And so there's this constant coordination and optimization. And if you can get an easier way to optimize it, where the AI will come in and figure that out, that will make it a lot better. And especially if you can do, this is what I'd love to see happen, is when we are able to train Optimus by showing Optimus what to do. I wish we could do the same thing with the IR robots. There's no reason why the IR robots cannot then use that programming paradigm. Because today, if I have a piece that needs to be welded, I can throw it down on a table. And if I have an expert welder and I can come over and just, weld this part, and he'll examine it and then know exactly what has to be done. Now, he might consult a couple engineering drawings here to confirm the type of weld he might there, but he's probably already got the instincts to know whether that's supposed to be a stitch weld, whether it's a 1/4-inch fillet or an 1/8-inch fillet, whatever it is they have to do. He'll probably know, and if not, he'll know what resource to check. Right now, you throw that thing down in front of an industrial robot, and it just sits there and doesn't do anything. So a guy's got to go over, and he's got to get this thing, what we call a teach pendant with a joystick, and lead the thing over, lead by teach, get in there, eyeball it. Yeah, that point looks good. Store. And then he's got to drag it along over there, store that point. Replay it. Does it look like it's moving right? Oh, that's not quite right. And then he goes in, there's a bunch of tests, and the quality of the weld's not so good. And what do I have to do? The weld parameters. It's very, very tedious going through that again and again and again. I just want to throw the part down and say, all right, you know what to do, right? I don't even have to explain it. Maybe the first time I show off, them, hey, come over here. This is what welding is like. Yeah, you want to do a little bit of a drag at a 15-degree angle because it gives you the best quality. When you come in here, you're going to just have to rake it a little bit to make sure it comes in. Eventually, it'll understand that. But we can't do that. So Today, when you look at those robots that are there, you're seeing a lot of metal. And you must think, wow, that's really costly. It's like, yeah, those robots are costly. But the tooling on the end of those things actually costs more than the arms themselves. And then all the safety fencing you put around there probably also costs as much as the robots themselves. You get all that stuff in there. Then you got the guys you got to hire to come in and program those things. They might also be 25 to 50% of the budget for that cell. Just the cost of someone going in and programming it and coordinating it and making sure it all gets together and fits together. So there's lots of room for improvement in the efficiency and the time it takes you to set up the process to get it going. And then there's the other of compressing it. And there has been a lot of effort. GM over the years, I remember back in the 80s, they came up with this thing called RoboGuide. I think it was in combination with Kamau, where's the idea of making this gate that you could put the robots in and hang them upside down so they could fit in. So rather than just having 4 robots, suddenly we were looking at, we might be able to have 6 or 8 robots being able to go in there and do a process. And that was already trying to compactify everything, but you can see we can compactify a lot more. If we get to 24, 32 robots in one cell, that's going to be pretty impressive. But it might
seems like a good place for just a second to, I want to come back to AI, but also to talk about the impact of the Unboxed process on density, that, if you're working on smaller and smaller components and then bringing those together later on in the process, instead of continuing, instead of the manufacturing being done in a line where you've got all the parts that are continually being worked on the overall entire unit as it progresses down the line. Now we're creating parallelism. We're working on the trunk. We're working on the hood. We're working on the sides. We've got the center of the vehicle that can be worked on from the battery pack. We're splitting up these individual component pieces, and we're able to work on them in parallel streams and then bring them together later on in the process. What impact is that going to have on your overall density of operations, and your ability to, either have more robots working on one piece at the same time, or, the secondary option of just creating more parallel cells for a process to be fed through, to where if you've only got the ability to get one part through every minute, but you need 5, that you could create 5 parallel cells that can all do that. Exactly. So you can expand and then recontract the part flow. So just talk about that for a second.
James, or you want me to take it, Hans?
Well, I figured I'd do the AI parts of the stuff.
Oh, okay.
You have a lot more direct experience with robots in a factory. So the spatial packing, it's, if you get I imagine there's this point in not too far in the future where, because the software, the AI it's ramping really fast, especially really recently. There's a couple of capabilities that if you get them, you can make some pretty dramatic changes to a factory. One of them is having reliable spatial awareness, like having a bunch of cameras in a factory and the camera just knowing where everything is inside the factory, right? So maybe you've got an overall controller, maybe individual robots have a set of cameras around there, but they know where they are and they know what they're supposed to be doing. So that's one thing. The other is spatial planning. Planning is not a difficult thing if you're able to create the problem, if you're able to define the problem in a particular way. But new AI techniques are allowing much more efficient planning. What planning is basically searching through the space of what sequence of things can I do to get a particular result, and essentially planning all the different sequences that you could do to pick the ones that are most efficient or safest or optimizing for whatever you want, instead of having to search the tree of possibilities, which is the classic way of doing it. Neural networks introduce this possibility, kind of like in Go playing, where you don't have to play out all the different possibilities in order to figure out what a good outcome is. A neural network gets trained up so it has a pretty good sense of where to start, and as it works its way through the process, it knows things that probably aren't going to. So essentially, it pre-prunes a tree for you, and can much more quickly get a set of planning. So if you have good spatial perception and you have good planning, now the dynamic of the robots that we have in the factory, robots we have in factories today, they're kind of a compromise between full automation, like the bottling factory, where it only makes bottles and can't do anything. If you want your factory to be a little bit more flexible, but you want to buy a mass-produced robot where you just get a bunch, well, then you can, an arm is kind of the simplest thing that can be mass-produced. You get one that's a certain size, has a certain, scale that it can work at. You get it in your factory, and it can substitute for all these custom machines potentially. It wouldn't be as fast. It might not be as cheap. But it's flexible, so you can get your factory up quickly, and your factory now becomes adaptable because people can go in, reprogram the robots. You can make changes. It's much more flexible than the bottling factory is, right? But a big constraint on how we use those robots right now is that they're basically blind, as Scott's mentioned before, right? You have to figure out exactly what all the precise movements are, and the way the robots have to be made. The reason that there's these giant hulking things is because in order to get precision, you have to make the robot arm incredibly stiff because it doesn't have any feedback aside from the stepper motors are saying, yeah, you're at that angle. When, the arm knows it's at this position because it's blind. So one of the other things spatial awareness gets you is now the robot arms, they have visual feedback on what they're doing. Potentially they have visual feedback on what they're doing. So now the robot arms get a lot cheaper. Because you don't have to make them as stiff. They can be much, much lighter. You achieve your precision through feedback rather than precision by making a precision machine. So now the robot arms, a robot arm that does the same thing gets smaller, it gets lighter, you can put more of them in a space. When you have spatial awareness, there's another trick that you can do. Like right now, we bolt the robots to the floor. You don't want them to move. Once you got them programmed relative to the fixtures, like you don't want them to move. You got spatial awareness and feedback, you put them all on wheels, right? So when you're getting your cell set up, you spread the cell out, they all get doing their thing, and then you can gradually optimize the thing by just telling them all to move closer. Your factory becomes more reconfigurable because instead of having, your flexible robots all bolted in spots, with fixed spacing and all that kind of stuff, they become dynamically configurable. So we're not that far away from having good spatial awareness and a good ability to plan and prune a tree to do this kind of stuff. So I can imagine like this intermediate before we get to the alien dreadnought, getting to a factory that is a lot more flexible than the factories that we have right now in terms of being able to be dynamic and optimize itself and flexible to its inputs, its outputs, its run rate, all that kind of stuff. I think AI gets us that probably pretty soon now. Like this is not 50 years in the future. This is 10, maybe.
From a sensor standpoint, is that the spatial awareness down to say millimeter or even sub-millimeter accuracy? Is that something that we can get from vision, or do we need LiDAR and other sensors in order to get that level of accuracy?
Vision is cameras are unbelievably good. Now of course, if you got a big robot arm and you want to position it down to, millimeter or sub-millimeter accuracy, you do have this overall problem that, it has vibrational modes and you have feedback controls. And there are certain mechanical constraints on being able to do that. But, if you put a camera on the end of the robot arm and it's got a microscope that looks at that tip, you can get your feedback, your positional feedback to whatever precision that you want. Integrated circuits, we do positional feedback literally down to like the 5 nanometers or something like that. Like we know how to do that in terms of the optics, the cameras, so that the actuators are a little more complicated and there are mechanical limitations, but getting that just from a sense standpoint is that like the sensors. And one of the reasons that a lot of this is taking a while is because cameras are such a great sensor, but they're so hard to process. Like if you've done, I'm sure Scott's worked on automation processes where you have a camera and, if you're using traditional vision algorithms, you kind of get the thing working and then somebody changes a light bulb in the factory, right? Literally things like a light bulb changing or a light bulb burning out or a blinking LED someplace, you tune up these algorithms and traditional vision algorithms, they can be pretty brittle, but neural networks, a little more training, and they can deal with all this noise and subjectivity, in the environment and still operate normally. And the other really exciting thing that we're just starting to learn this recently, and like the possibility has been there for a long time, but we're starting to see people actually do it, is be able to have these self-supervised large models used to do planning in an environment. And it so happens that the way that we've discovered this capability is through large language models. So you get this thing where you've got language integrated with planning suddenly. Like Google has demonstrated this on a couple of big models now, where essentially without training a robot, a specific set of motions, you can use a language model coupled, some actuators and some other, world modeling and a vision model. And all of a sudden the system, it becomes general enough that you can give it instructions like verbally in English. And it can actually put together a plan and turn that into a set of motions for actuators. And the fact that that's doable now with systems that aren't even really designed to do it, because the AI has got to that level of generality, like it seems really likely that sooner rather than later, we're going to get to the point where Scott can go, where, you can get rid of all the barriers and Scott can have his, KUKA robot arms or whatever the deal is, whatever they have at that particular point in time. And, and instead of having to show the robot, you tell the robot what to do. I was like, put the welder down here and I want you to run a thing like that. So just that training gets a lot easier once your planning is getting done by an AI and your interface is at the sort of, is at a much more abstracted level inside the thing. This is great. There's so many great things that are going to happen with this stuff in the next few years.
Yeah,
if it's true that Tesla has developed, like the FSD is supposedly basically something that came out of the automation that they wanted to do in the factory. I think they called it the bamboo road, where they were trying to get every car to put itself through its own battery of all the safety testing that was required by whatever regulatory agencies. I'm sure some of them are NHTSA. I'm sure some of them are some other things. And they wanted to be able to qualify every single vehicle so that they could make changes on the fly. Any vehicle could have any different part put on it. That way they didn't have to operate in huge batches like traditional manufacturing processes do. That it seems like the factory really then is the place that a lot of the AI and automation work starts. And if going back to if the factory is the process, how much is that going to continue to be the case for Tesla? Like, is the Tesla factory going to be at basically the leading edge of real world AI, or is it still going to stay? I mean, do we think it's more out in the broader world with FSD and Optimus Bot, or is the factory itself going to be the bleeding edge of that development work?
I think a factory for doing this kind of stuff, to be a company that has a factory is like a gift for people who want to make the transition from the laboratory to the real world. Because factories, just as we were talking, factories today, you can make them arbitrarily constrained, like these robot cells that Scott was talking about. They're constrained to the millimeter, like all the physical positions and everything, like that's super constrained. On the other hand, you have factories, which is like a bunch of people sitting at a table and they're handing parts back and forth. Modern factories frequently have a blend of these things, right? So you've got this canned environment that you control, like all the safety and all that stuff that you can deal with. And you can dial up or dial down the generality. Like you can have more or less controls for this stuff as you're developing the technology. So having a factory that you can try to solve real problems to real purpose is such a great asset for a robot development team to have, especially if you've got a really big factory, because you do get to a point when you're developing stuff where you really want to run 40 or 50 of these robots. You don't want just one. Like, you gather more data, you get more experience, you can try more variation. The bigger your factory is, the more robots it can absorb and keep busy and exercise to help the team sort of get up to speed. I think Tesla having a lot of big factories while they're developing a robot, that's actually, those two things are so synergistic in terms of feeding back off of one another and accelerating the progress, both the progress towards making robots useful for the factory, like from the factory's perspective, and also from the perspective of making the robots more and more capable over time. So I think long-term AI, it will end up playing a huge role. And I think in the short term, the factory is a huge asset to a company that's developing robots.
Yeah, I think what you're going to get is this incredible flywheel that will allow you to keep improving the factory faster than you could, because early on there were not very good planning tools. The robots kind of arrived, and then everyone just figured out, well, where would you put the robots? And they kind of guessed, well, over here might be all right. And then you start programming, you find out it's wrong, which means you now maybe have to move the robot somewhere else, or you just keep on guessing. So eventually it's like, well, we're going to use CAD and some sort of planning tools where you have what we call a digital factory. And that's when you're kind of in this God mode that you can easily change anything. You say, well, what if the robot's here? What if it's a robot here? And it's like really easy to find the locations where the height's going to be to optimize it. But once you decide, oh, okay, that's where they're going to be, and you go out there and you bolt them down on the floor, it's not so easy to go and move them. You know, you're going to have to shut the line down for a little bit. Some guys are going to have to come out, and you're going to have to drill some more holes in the floor. And like, you know, how many times can you keep on drilling holes in the floor without having to patch them? So you want to get it right as best as you can. And of course, the reason they're bolted down is that you need that repeatability that comes from the rigidity of the robot. The fact the robot doesn't see anything, but it's just able to always go to the same location again and again. And again, in the early days, they were afraid of the robots crashing into each other. So you just made sure they weren't in each other's workspace, which meant you didn't really get the density that you wanted. And then they started getting braver and started getting them closer. But to do that, you need to coordinate them. And either you do it that you hope they both do the ballet at the same time with the eyes closed. They know the dance steps, and they do all that, and they're kind of out of the way when cycles start and goes on there. Or you start doing something that when you begin to get into where our workspaces overlap, we will send a signal which tells you don't enter, get out of the way. And they start doing more and more as they get closer and closer together. So that is going on, but the AI will be a little bit better because it can have the overview. They can all understand what's going on. They can see what's going. And I think we've all seen those comedy routines where someone's like walking through a construction site, and the guy's like, you know, carrying these big heavy things going around the lumber, and these guys just kind of know when to duck their head, and it kind of swings around and comes up. And it's like no one is paying attention, yet no one is getting injured, even though they should. And that's what the factory's going to be like, because all the bots are going to know what's going on. Right now, it's a bit tricky that they don't have, it's all very centralized when it should probably be a bit more decentralized, and that there is a cell controller that is basically the conductor that's telling every instrument when to play, what the notes are, and all that, as opposed to everyone sort of ad-libbing as they're going along, because they're getting something that they know this arm is going to swing on over here, because either they remember it's there, or they kind of are able to peer into that controller and say, oh, guess what? Its move is going to be over here. I plan on being there. Maybe I need a duck to get underneath. And the Shanghai video was a pretty good video, because I think I almost have to call it, it's like this bucket brigade that's going on as far as the part movement, that we see the operator loading these two small pieces of sheet metal that's going to go over to a robotic cell for welding. So those pieces then have to be brought over so the robots can weld it together. But he's handing it off to a robot, so that robot can pick it up to bring it over to the other robots. So it's not even directly going into the cell. It's like this other one is doing that. And you can already see, well, that's kind of inefficient, isn't it? That the work is being done way over here, and the humans have to be off at a different location in order to make sure they're out of the way of the robots. So once those barriers start to drop down, the landscape shifts, and things start to become more compact, and Optimus can start doing operations that a human could do today, but you just can't do it because it's too dangerous. And a human could do it, and they could do it successfully for like an hour or 2 hours, and then they get tired. and then they forget their dance steps, and then suddenly disaster happens. But when you start to have a robot, you don't have to worry about things like that, because they are going to know what's going on. And I think this is at Famous there, that yellow robot there does nothing but pick up the piece and bring it over to the other cells. That's all it's going to do. So that costs as much as a car, that yellow robot there, along with the end of arm tooling and everything else, maybe a little bit more. So you're paying for a Model Y just to pick up the sheet metal that goes from there over to the other place. That's definitely a cost you could reduce by not even having to have that operation in the first place.
Yeah, and you can see that even the operator has very constrained ability to, like he has to walk out of the cell, hit the button saying I'm out of the cell, and then the robot can move or something like that. But whenever the operator moves into that zone where he's within reach of the robot, he has to clock into that space and clock out of that space on every operation from a safety standpoint. And that's because the robots are like, they're blind, right? They don't know if there's a human in the space, and they're really strong. So that's
Did you notice he made a mistake? If you go back that, you'll see the operator jumped the gun.
Yeah.
So he was supposed to wait for the green light, but he went in before the green light. And because he broke the barrier, that robot stopped, and he had to go back and reset to go in again. So that's an example that it's so easy, but because it's so repetitive that even the operator screwed up what would seem like something very simple.
I bet they hardly ever screw up. Having a camera looking at you is probably
maybe that's what it was. But it just kind of shows that, there he went along, he made that mistake, but that mistake is okay because he's nowhere near the robot. But imagine he really was supposed to be in the cell where the robots are moving around, and they're not going to stop because time efficiency and everything. And the operator just has to be on top of his game to just make that little mistake.
And spatial awareness this will be one of the first things to fall when spatial awareness comes to the factory, right? Like the operator will walk up, he'll put this stuff down. It'll become so much safer to be close to the robot. Just like, FSD, we have all
there
pedestrian detection. Yeah.
See, he went in too soon. Got to reset it. See, that robot froze because, wait a minute, you're not supposed to be there.
There's a sensor that if he occupies the cell, everything stops moving.
Yes. And you see that standoff distance? Yeah. You see, why that is so deep? Because the robot has to be able to stop in the time it would take a human to sprint that distance and jump through the air.
Yeah.
So as soon as that beam is broken, if they're coming in a full sprint, it has to stop.
Yep.
That's the only reason. It's like for no other reason except safety. It's
and that's a lot of space.
Reasons or
it's getting spent.
A lot of space.
On the fact that we have these super powerful robots that are not super smart right now, or they're not super aware of their surroundings is probably a better way of putting it. And that's very fixable. So we have an Amazon Fresh, one of these new grocery stores I've been shopping at recently. It just opened up, and it's one of these ones where you go to the store and you just get your bag, you walk around the store, you put stuff in the bag, and you leave, right? That's all you do. If you look at the ceiling, there's just like cameras freaking everywhere. And so, there's still human operators and that kind of stuff. But for the most part, it's a store. It's got an AI. It has spatial awareness of where all the products are. So if you as a human walk in, you touch a button with your phone code or whatever, say, this is my account. It follows you around the inside of the factory or the store. Anything you put in your bag, it bills to you. If you take something out of your bag and you put it back on the shelf, it knows that and it unbills, and then you just walk out. There's no checking out process at all. So this is a real world example of organizations already making a lot of progress on this spatial awareness thing. We have these sloppy, complicated humans with their weird clothes and their 40 different kinds of shopping bags. And you've got all these products on the shelf in all these shapes and sizes and stuff and, everywhere. And yet with all of that complexity and all of this sort of dynamic unpredictability that human beings build to it, Amazon's already demonstrating that they can build a space that has sufficient awareness that people can just walk in, pick up what they want off the shelf and leave, and it works. So this, if you do that in a factory, you make a lot of progress toward the thing that we're talking about right now.
Yeah. So they're not scanning a barcode or UPC or anything like that.
No.
Amazing.
There's you just walk. So yeah, if you get one of these, you should go check it out. It's a fun experience, especially if you're an AI person, because you just go in and you just pick stuff off shelves and you put it in your paper bag or you put it in your pocket or whatever, and you leave. There are no constraints on what you do. You have to, you use your phone to clock in and clock out of the thing. So that's when your shopping session starts and ends. And so it has an account that it's going to charge the stuff to when you go in. Although they have just started adding a one where you can register with Amazon, you register your palm print. And so when you walk in, you put your palm on the palm print reader, and then it's like a little subway gate thing. You walk in, you hit with the palm print, you walk in, pick all the stuff you want. When you leave, you hit the palm print thing again, and then you just walk out of the store. And it's using vision to track all the products, track all the people, figure out who's picking up what. I went down there. I went to the store with Karen, and this was actually kind of cool. I clocked in just with my ID. Both of us walked in at the same time, and we went around, picked up stuff, right? Put it in 2 different bags, and then we both walked out together. We clocked out together when we left the thing. And the system was smart enough to figure out, oh, these two people are effectively one person. And so all the stuff that either of them do, I'll count that against one. Like I was worried that might actually add some complexity, and it handled it with no problem. So, I mean, we're getting there. The tech is getting really close to being able to like change this factory dynamic, I think.
So with those, well, I've got a couple of questions here. Maybe this would be a good time for some of the listeners to be able to inject some questions. Looking at Optimus specifically, we saw that obviously they did the grasp that was completely end-to-end as far as images to joint angles controlled by the neural nets. So that tells us that we're still, relatively early on in the development of Optimus as far as its ability to control itself in a way that a human would, and for the responsive, flexible neural net architecture to be able to interact with the environment in a non-discretely programmed way, like we've been saying that a lot of the industrial robots are programmed. So what do you see as the timeline for the software development of Optimus to really be useful as a product that they could potentially sell outside of the factory?
All of these things, it depends on how much emphasis you put on a particular goal, how soon you get to that, because they've got multiple goals, right? I mean, they might want to sell some Optimi out in the world at some level of functionality, but they also want to get to higher levels of functionality. And to some extent, with limited resources, you've got a tension between these two things, right? The more you shoot for easy things that you want the robot to be able to do in the world, the sooner you can push it out the door. But the more that becomes an impediment to making rapid progress against getting to higher levels. So this could work out a lot of different ways, depending on what Tesla thinks is kind of optimal to their goals overall. Like, FSD is a pretty good example of this, right? They could have waited long on any particular version of FSD. They can always wait longer and refine it more before they give it to people. But you get a bunch of stuff when you give it to people, not the least of which is happy customers who have a better system. So there are all of these different things that you can trade off. And you can legitimately say, well, they should have held back on this feature, or they should have given it to people sooner. Those are, it's the spectrum of things. So it's a hard question to answer because it requires you to speculate about what Tesla thinks those trade-offs are and how those trade-offs are manifesting in their development process and the feature set that they can give to customers. Optimus can be the same thing. In fact, Optimus is going to be much more like this in a lot of respects, in the early days especially, because you can, if you wait a year, you can deliver a much better product if you just focus on developing the core tech. Now, once your core technology gets to a level where what you really need to push it further is to gather a lot of data, that gives you another incentive to let's come up with some applications in the real world that we can push this thing out, because that will feed back into the development process. If you push a product out too early, then that actually slows your development process down in ways, because now customers start having problems, and now you have to devote a lot of resources to dealing with the immediate problems of the customer on this temporary product that that you're going to supersede in the near future. So, going public or trying to push the product out to consumers, it's this two-edged sword. On the one hand, it gets you tons of advantages in certain respects. On the other hand, it can take a lot of resources, especially if you're not well prepared, if you're not very polished. And it's the kind of thing that needs a lot of polish, for customers to be able to make use of it. I mean, and once again, FSD is a really good example of this thing happening. Optimus, it'll have that set of trade-offs too. And Tesla could decide to push it out, to have it do simple things and have that be sooner, or they could decide to wait longer. I think for private people to get a flexible Optimus that you're going to bring to your small factory, or you're going to bring to your home, and you're going to do a little bit of training, I think that's going to be a while, because it's so much easier for them to just work with bigger factories that have more dynamically constrainable environments that are more flexible. You have fewer points of interface. You get professional feedback, because the people you're dealing with, they're pros. And basically
the ROI
demand,
on replacing the labor in a factory like that is much higher as well.
Yeah, the ROI is super high on it. So, and in a sense, it's a much easier problem with a higher ROI, and you get better data, right? Once you go to the customers, the ROI is a lot lower. The TAM is much bigger, right? I mean, the TAM for, all private robots in the world will be much bigger than the TAM for like all factory robots. But the thing is, the TAM for factory robots is so huge that you can just keep shipping robots into factories for a really, really long time before you really need to, in fact, probably the first consumer things they'll also be test things. It's like, we're going to give everybody in this small town robots, and we're going to have, and we're going to try the, folding laundry, walking the dog, doing the dishes kind of stuff. Really, those are really, really, really hard problems. Dynamic, like matching what a human being can do. It's a much higher bar. Like we're, being human beings occupying the world, we're used to our bodies, we're used to other people and that kind of stuff. And we take them for granted. But walking is a miracle. Like it's an amazingly complicated thing. And every human can do it. And we can do it really well. We can walk, we can run on uneven ground. We can go up and down stairs. We can hop along on one foot. We're super flexible and dynamic. Getting there with robots is that it's a high hurdle. But long before we get there, you can make robots useful.
Yeah, I kind of agree is that Tesla already has a built-in use case and the built-in customers, and they know what they want to do. So the task they're focusing on is what they're seeing in the factory. And the last time I was in a factory, at least an automotive factory, folding the laundry and making crepes is not something that you need a robot to do or anyone to do. But for home use, that's what people are going to be expecting. It needs to be able to do the laundry. It needs to be able to cook and wash and do a bunch of these other things that are just completely different use cases. Now, it may be that it's just almost, snap of the fingers that it happens, that once they've figured out how to train this thing, it's just a matter of showing it like, here's how you fold laundry and it's done, if they're able to get there. But that's not their focus because they don't need an external customer right now. A lot of the other robot companies or humanoid robot vendors, they do because they need the cash flow. They're just operating on venture capital right now and nothing else. Tesla doesn't have to do it because they can justify for the return on investment internally, and they can slow walk the whole thing until they're ready. And then my suspicion is that the first users outside of Tesla will probably be their sub-supplier network because they're going to be very, very similar. However, they may be encountering situations down there that are very different than they're seeing in the factory. So there's like really no small parts that are assembled inside the Tesla factory. That's all coming from the sub-suppliers. So that might be the first time they're kind of exposed to that. So suddenly Optimus has to have a little bit more dexterity or maybe less mobility because it might be one of these lines where things are just coming down and all you're doing is just operating the same place. So they may be looking at that problem a little bit differently and thinking about it. And that's going to be important in the alien dreadnought because everyone asks, why are the robots, why are they mobile? Why don't they have wheels? Why do they have to be mobile at all? And it's like different use cases. There are times it doesn't need to have feet. It doesn't need to be mobile. There are times that maybe putting on it would be a good idea, but I think the answer to the question for the wheels is just ask the CEO of Boston Dynamics and what he said to Lex a few weeks ago, because they had the handle robot, which I thought was like a really cool robot. You may have seen that, James. It was like the Boston Dynamics robot that's actually on wheels, that's taking boxes out of shelves and going over and doing palletizing. And it was really kind of fast and moving around. It was like an ostrich because it had this big tail that was a counterbalance. And it ended up, even though it looked like it was really fast, it was too slow for the operations because it had so much dynamic motion going on that when the robot would get over to where it needed to be positioned and the arm would move, the whole thing would kind of shake. So the wheels were constantly trying to adjust to keep the robot steady so it could go ahead and do a particular operation. So when it actually was placing the box or trying to grab the box, it was slow because it was trying to stabilize itself. But once it had it, it could scoot on over to wherever it needed to be. The problem is the situation they're showing is really contrived because no one puts the pallet over there and when the shelves are over here and then having things running back and forth. No, you tell the fork truck, bring it right here so I can just pick it up and turn around and start dropping it in.
That's actually a pretty good example of the thing you were talking about. The robot had these physical limitations. Like it had these modes, which, you know, to the best of my knowledge, Boston Dynamics, they're not AI heavy. They're more like straightforward programming. So I don't know their process super well, but this is what I understand about what's going on. And this is the kind of thing that training like an AI control system for the robot actually, you know, it can solve this problem. Not all the time. Most of the time it can solve this problem without you having to change the robot, because its ability to predict, you know, what's going to happen when it does a particular series of actuations is more precise than what you can easily capture in a physics-based model, right? All of the weird things like, oh, this tire's a little low on air and the you know, it's tilted, or I just ran, or somebody left a quarter on and I'm slightly tilted relative to, you know, we already build motion control. Neural networks for bodies. They can do all kinds of crazy stuff they're highly adaptable. Like the ground can be uneven, it can be gravel, and you can still operate because it has the control scheme for the robot is just so much more sophisticated. It can take in so many more inputs over a much wider range of things, and it's much better at predicting an outcome. So even if you have a resonant mode or flexibility or imprecision, you add some cameras, you get some feedback, and then the neural network can adapt to all of those things. So, you know, if I were watching that, I didn't see the video, but like, that's the kind of thing where I like, see, you should use a neural network because then the constraints of the robot, these modal issues with motion and whatnot, it's less of an issue because the robot just learns to slow down, to damp the motion instead of having, you know, rigid programmed actions.
Yeah, absolutely. So the integrating of the neural network into the entire motion of the bodies can be very important, because whenever you move one arm, you have a consequences going throughout your whole body that you may not be aware of. And depending upon what you're lifting up and how hard you're moving, it may be that suddenly you have a lot of torque on your feet to keep your balance, and you've got to move your pelvis or something else. But it's very slow. You might look at it and say, oh, there's no consequence. And that's why it's kind of called dynamic. And if that motion, somehow you already know ahead of time the consequence of that motion, you can react much faster and you get that fluidity. And that's what the human body is so good at, is that we do not consider ourselves to be an assembly of 5 limbs. We consider ourselves to be an entire body. And so when one thing moves, we know exactly what the other part has to do to make sure it's smooth. And that's what's really hard to do with heuristics, because the only way to solve things heuristically is you break things down into really small chunks. So you can deal with that and you deal with the other, and then you sort of figure out, well, how do I actually bring the two together so that the system now kind of resolves itself? And it resolves itself, but in a suboptimal way.
Yeah, your heuristic's always going to have some assumptions built in, some constraints, and you solve the problem inside that heuristic envelope. And now there are these kind of constraints that you built into the system to make it decomposable, so it was easy to understand, explain, build rules about. But now they become a barrier to like efficiently optimizing the thing overall. And yeah, a human body doesn't have that, right?
Yeah,
you got literally, you know, tens of thousands of nerves running from your motor. Like muscles aren't individual muscles. Like muscles are made up of lots of muscle fibers, and each one of them is separately controlled by your brain. So the number of sort of individual control elements that your body has is just absurdly large, and yet it moves so smoothly, right? It's and dynamic, and with feedback, it's great. Yeah, and our robots are totally going to be able to do that. This is all stuff where the proof of concepts have been done. Like, this isn't technology where we need a breakthrough or something. This is all turn the crank. We just got to productize the technology. Like every single thing that we're talking about in here, it's been done. It's been demonstrated. We know how to do it. We want to refine the technique to the point that we can push it out into real products. And I, you know, that's not easy. I don't want to shake it off. You know, it's real work, but it's not like, it's not risky in the sense that it's not going to happen, or that we need, you know, unforeseen things to occur, or that it's not brittle. I mean, these things are definitely happening. Like the proof of concepts for all the stuff we're talking about here, they've been done.
Well, and it sounds like something that we we still need a lot of humans in the loop to make that transition. And so, I guess going back to the idea of the alien dreadnought, like there is no alien dreadnought for quite some time because, maybe the human's role in the factory is different. Maybe instead of doing operations, they're teaching operations, but there's a long, road left of that transition and migrating tasks from human operators to robotic operators. And if Giga Mexico is built from the ground up for the Unboxed process, and Optimus is supposed to be part of that Unboxed process, it seems like that's the logical, basically, hub for this innovation of this next step of manufacturing technology and transitioning more and more intelligence, not only to Optimus bots, but then back into industrial robots like we've been talking about. Do we have a few more minutes, or do we need to go ahead and have a hard stop here? We're coming up on 11 o'clock for you, James, and 2 o'clock for you, Scott.
I have no hard stops.
I can go another half hour.
Okay, cool. So, yeah, is there something that you want to build on there, Scott?
Yeah, I wanted to ask James a question that I assume you're familiar with the Optimus video from the shareholder meeting. And the tweet that came out sort of alongside it saying that yesterday was the first time they did an end-to-end pick, and I think we can see exactly when it was because they said it was in there. You could see the one engineer putting his arms up like they scored a touchdown. The same, something very simple. Optimus went over and picked up something, and that seems to be a very important moment. And from here, do you see like this really rapid S curve of them being able to train tasks? Or do you think it's still going to take a little while before they can get to the point that they can start training lots and lots of different operations and tasks for it? Is there still a lot more work they have to do?
My impression is that was an important moment for that engineer who'd been working on this task and trying to, I don't know if did you look at the object it was picking up? It had a very weird
potato.
shape.
Yeah.
No, it was, well, I don't know. I'd have to go back and look, but my perception was that, it's kind of, it's this very oddly shaped thing that figuring out the right grasp, for it in a particular orientation and getting it up off the table, without dropping it and getting it into the orientation you want in order to put it in the box. Like that's not a trivial thing. Optimus is a brand new robot and it's got brand new software. So a lot of these like little, yay, we got it working things is not because, now you're going to go write a paper on it, right? Like this stuff has all been done before, right? But these guys haven't done it on Optimus, and every step they get is a nice step forward for them in terms of like getting their capabilities there. And I think, most of the stuff that Tesla's doing on Optimus right now, they're not breaking new ground in like a robot control. They've got this new robot and they're getting the basics working on it right now. And that's kind of the level that they're at. I think in time they will be breaking new ground on robots, but it's brand new. And for the time being, almost all the capabilities that they want right now, there are these existence proofs for the basic techniques to do it. Let's get that technique, put it on the robot, get it working, see how well it works, come up with ideas for refinement. Maybe eventually we sub it out and we come up with a better idea and we do that. But they still haven't got all of the things that exist in the world that would be useful to robot ported to Optimus and working on it right now. So I imagine they're going to be doing that for a while. And I think that's what they're always doing. Like this arbitrary grasp thing, like this is Amazon has had this thing going for a long time about wanting to get picking robots, right? Because that's a constraint on them in terms of like, how efficient their operation is. And they've spent, they have an internal robotics group that just works on robots for picking stuff off of shelves and putting it in boxes or vice versa. They sponsor this competition every year where they invite all these university teams and startups to come, and try to essentially, compete to be able to just pick things off of, and a lot of that comes down to, well, how do I pick up this arbitrary object in the real world, grasp it in a way that doesn't damage it, and then maneuver it out of a shelf or a box and into another box? Like that's a pretty complicated problem. So there's a lot of research and a lot of practical real world work that's been done on this. So Optimus wants to be able to do all of those things, but the right place for them to start is to look at other people's ideas, try those out, see how they work, see how they can improve on them, integrate it into the other things that they want to do and move forward. And I would guess they're almost entirely at that phase right now, where they're just getting the stuff in and trying to understand how it all interacts. Autopilot went through a long phase like this, where they were essentially doing the obvious stuff and getting it working before they started breaking new ground, doing stuff that you really could honestly consider research. So Optimus isn't there yet. My guess is they'll be moving into that territory as they get it kind of polished up. But we'll see Optimus walking around like more smoothly, and we'll be able to see it do basic, more of be pretty solid with basic grasping and that kind of stuff. And at that point, now they're going to have to start breaking new ground, right? Because then they'll have caught up to what is already known for how to do stuff in robots. They'll have to make up new stuff. So I don't think they're there yet. And I would guess they're, 6 months to 18 months away from generally having to, essentially figure out entirely new stuff in order to keep pushing Optimus forward.
Yeah, I would think being able to teach Optimus new tasks really quickly, that's probably going to be where they're breaking a lot of new ground.
That
for sure.
That would. Yeah. And this might be why they're getting people with large language model skills coming in, right? Mm-hmm. Because surprisingly, large language models have turned out to have this capability in a shockingly general way. And that's a new research topic. Like, it's not well understood, like why they can do this and what the limitations are. But if it turns out to be as flexible and powerful as many other surprising characteristics of large language models, well, that's something you really want to double down on, right? Because it's one tool that can be built and polished in a fairly straightforward way. And it's super flexible. It can solve all these different problems. We're kind of like, Chat GPT can do, like, how many different things can it do? And yet it's just, all it did was predict the next token, right? Like, it's a simple, straightforward training thing. And yet it opens up this whole world of possibilities in terms of things you can suddenly do. There's definitely some potential for that to play a role in planning and not spatial perception. I mean, spatial perception, it could be done, but it's not the best way to do it because we have other ways of doing that. But planning and the interface to people, mimicking what people do, like language models, they just mimic the text that they've seen in the world, right? So doing a language model, a similar kind of thing to get a robot to mimic what people do, like that's a viable possibility. And it hasn't really been looked at right now, but it would be super powerful, so that's research, getting that stuff done. So I agree, Scott, that like the mimic stuff, there's space there.
Do you expect the GPT style LLMs to be able to, once they're expanded into multimodality and they actually have visual perception, and you expect that to be able to just physically show the robot something? And not necessarily, I mean, you could use words or a combination of words, but also visual input. Just say, hey, like, I want you to pick this up, grab it, move it over here, set it down. Is that something that a GPT should be able to process and feed into Optimus or an industrial robot at the not too distant future?
There are definitely roles that an LLM could play in that, and it might be able to play the whole role. There are aspects of this thing that you just described that haven't been done, and that where it's parallel to, but not identical to, the things that LLMs are doing right now. So there could be some glitches getting that working. As far as the voice interface and, conveying a concept, conveying to the thing what you want, like, we'll definitely use LLMs for that. They're just so good at that task right now. As far as the using an LLM-like process, so a large language model is, it's a transformer, and it's trained in a self-supervised manner, which is basically, you just have lots of text. No human has labeled this text. You just have all this text, right? And you can just basically feed the text into the thing, and it learns just from the text. And the way it does it is, when you train it, you give it, 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, when you train it, you give it 10 inputs, and it learns just from the text. And the way it does it is, an incomplete, you take a sample of text that you want to train on, and you remove some of the words, and you ask it to predict the ones that are missing. The way that GPT does it is it always removes all the words at the end of the sentence. So you start with the beginning and you keep asking it to predict successive words. But there are other ways of doing it where you give it a whole sentence and you take out 4 or 5 words at random and you ask it to predict them. That also works. It produces slightly different results. So because no human has to label this, you've got literally like absurd amounts of data. Like current language models on the scale of 40, 60 billion parameters are getting trained with 1.5 to 2 trillion tokens. And you can construct corpora that have 1.2 trillion unique tokens. Like they're publicly available ones that you can just basically download off the internet to do all this kind of stuff. So you just give them lots of data and they just learn this essentially pretty simple thing, which is predicting the next word in the sentence. But in order to do a good job of predicting the next word, you have to figure out all kinds of things about the world, right? Like the president of the United States is, well, there are a lot of things that are grammatically correct that can go in that space. You have to learn an awful lot to know the names of the presidents and have figured out who the current president is, right? So you can predict that. And the same thing with like all the other capabilities we see. Kind of amazingly, GPTs learn all kinds of practical real world skills just from trying to predict the next token. Okay, so similarly, it is likely that there's a parallel in motion training, right? But now you have to take the whole problem of text, predicting the next token, and turn that into predict what this human is going to do next, right? So tons and tons of YouTube video. Like if you can, and people are working on this problem, convert the YouTube video into motion with like humans doing stuff, right? And now let's train a transformer to predict the next thing that happens in this sequence of events. As a side effect of that, what the model should develop, if it's parallel to, and it likely is it should develop a predictable understanding of the world, a model of physics, an understanding of context, and all of this kind of stuff from being able to look at stuff. So in that sense, yeah, a transformer to predict the world. In a sense, Tesla's already trying to do this with some of the things that they're doing with FSD. And I think long-term they do. Like one of the reasons they want diffusion models and one of the reasons that they were playing with NeRFs before is because right now they got vision in. You got a picture that comes in and then it goes through this complicated thing that produces all these useful abstractions in the middle that you can use for driving the car. If at the end of that, you can turn it back into a picture, now you can just take lots of video and you can train it. You give it the video in and it has to produce the video out after going through all these intermediate abstractions that you do. So instead of having humans label all this data, you can close the loop on you just capture lots of video and you train it. And if it demonstrates the same level of power that we see GPTs doing with text, which is frankly shocking level of power that really nobody expected. Like if you had suggested that ChatGPT could do the things that it does to pretty much anybody in the world 5 years ago, like who knew anything about this stuff, they would have told you that you were high, right? There was no way that it was going to be that easy. It's turned out to be way too easy. If it turns out to be similarly easy for physical models, and we'd have no good reason to believe that it isn't, then yeah, we may be on the verge of a straightforward way of building foundational models for these things where they can learn all the stuff that they need to learn to have physical models and understand, cause and effect in the real world. And if you can build a model like that and you endow a robot with it, now you've really got something. Like you can tell it, put this over there. You can show it. It can see and understand what you're doing, predict the actions, relate it to its own. Even if it has a different number of arms or a different number of joints or whatever the thing is, understanding, the goal, extracting the goal from what you're doing and mimicking the action in a way that observes all of the common sense constraints that a human would place on an action. Don't break anything, don't move too fast, don't spend too long, just do the task the way I want you to do it without me even having to tell you all of the details. It should be possible.
You get my gears spinning. Thinking about how it would be applied. So instead of a large language model, we'd have either like a large motion model or a large gesture model. So your tokens are now predicting the next motion or the next gesture.
Yeah,
on everything.
This is what
and
you
it gets,
do.
yeah.
This is
now,
what
this
humans
gets
do.
frightening because
Yeah,
think
no,
about what's
like,
going to happen is it gets enough training data. Suddenly you've got Johnny 5.
yeah.
He's just going to be the wisecracking robot that's out on the factory floor,
Maybe,
just doing
yeah.
all these things.
He wants
and
to
just
be popular.
because
His objective
yeah,
function is life of the
because he
party.
knows a human, this is what the next gesture is going to be. Is, give me the high five,
Yeah.
do this and that. You know, see someone's go by, it's like, oh yeah, live long and prosper. You know, you just see all these kind of gestures that it's just going to start because that's all they are, tokens, right?
This
Tokens
is what
can be
every
words, or
human
tokens can be
does.
movement.
When you're an infant, infants open their eyes and they look at the world, and their brain starts trying to predict what's going to happen next. And you can see this in their behavior, right? What they're surprised by magic, even babies, they're surprised by magic tricks, right? Because they've developed enough of a model of the world that they know that shouldn't have happened. And the reason that they pay attention to it is, I need more data on this. I need more training data for this particular thing. Kids do it. Like, so we know that at some level that process works because human beings do this process, and it's fundamental to our understanding stuff. Like, it's, remember that Cybertruck video they had where they almost crashed the Cybertruck a whole bunch of times, and they keep stopping just before the crash. Well, what your brain is watching that, and it's predicting what's happening as it's doing that. It's fundamental to how we perceive stuff in the world is we constantly predict the next. When you walk up to your doorknob to turn the door to enter your house, if the doorknob is wet, you immediately notice it as soon as you put your hand on. Why? Because your brain was predicting it was going to dry. It was going to be dry, and you're surprised. Everything that deviates from your predictions, that's what draws your attention, right? And everything that doesn't deviate from your predictions, right? Like, you put on a pair of pants you've never worn before, and they're tight here and loose there and that kind of stuff, and you forget about it about 10 seconds later, right? Initially, you really notice it when you put the pants on because your brain was predicting what your old pants do, and now your new pants feel different. And then after a little while, it's like, okay, I got that. And it just shuts it off. Like, you become unaware of it. It's not like your body has stopped feeling that the pants feel different. It knows. It's just not bringing it to your attention anymore. We pay attention to what deviates most from our expectations. And in order to do that, we have to have expectations. We make predictions constantly. And it's very likely that this is essentially what we're going to do with these robots, where they're going to have a similar set of abilities. And large language models are turning out to be a framework for doing that works shockingly well in the real world.
So assuming that video is tokenizable, and then that we can do some sort of training with GPTs by masking the video or some sort of way to get the LLM to do predictions, or I guess, just call it a GPT if we're in the context of video, then that's a much higher bandwidth data stream than text, obviously. And so it seems like there is going to be a computational limit or constraint for the near term to be able to do that effectively and at large enough scale. So are we talking about something that is 2 years out based on how compute is scaling today? Or is that 5 years out? Like, how long before we can really effectively create the equivalent of ChatGPT that was trained on video?
So this using video and masking stuff, like, that's already done. People already use transformers. They feed video in, they block out parts of it, and they tell the transformer, guess what I covered up? And it works. We know it works. It is really computationally intensive, much more so than with text. We are learning tricks to make it much, much faster. Like, I would say it's gotten 100 or 1,000 times faster in the last couple of years. How long will it keep getting faster? So that's a good question. We don't know how much. We don't know where does that curve taper? Right. I mean, we've been getting fantastically more efficient at being able to do this training from video data. We don't know how long it'll keep, at some point it's going to taper, and because we'll have got all the low hanging fruit and the curves. We don't really know where that is right now. But at the flip side of it takes lots and lots of computation. Like this is not unrelated to why Tesla is making their data center 10x bigger this year and another 10x bigger the next. So it's like at the end of 2024, it's going to be 100 times as much compute capability as they had at the end of 2022. Like, that's, why do they need 100x compute? Because this is a big problem and it needs a lot of computers if you really want to do it. And so Tesla has a number of challenges that are compute intensive, but this thing we're talking about right now, I think this is really core. Like if they get to where they can close the loop on FSD, they can get a dramatically more capable foundational model for doing what the car does, or for doing what Optimus does, because it would be, it's a general model of the real world, this thing, once you get it trained up. And it's extremely likely we'll be able to do this from video, and we should be able to do it relatively soon. If Tesla has 100x the compute, even if the video training from video doesn't get dramatically better than it is today, they'll have the computers, right? It'll take a while, but they can do it. And if the techniques continue to improve, then it could happen sooner, right? You can always use that. The computers aren't going to waste. They're definitely going to get used. There's so many useful things to do with this stuff right now. They could move on to the alien dreadnought factory that we're talking about. Let's start training the factory foundation model, where where every arm is an arm of the factory, and every robot is a component of the factory's awareness of itself, and let it optimize the whole problem itself. Like that's probably a big problem, and it's going to take a while. But it's there, and it can be done. But being able to build the foundational models for reality, not just foundational models for text, which is what an LLM is. It's a foundational model you build. It has a foundational understanding of the language as read from books, and all of the information built into that. And that foundational model, you can build all these applications on top of it. It becomes the root of being able to do, like with ChatGPT, like almost anything, like shocking. The possibilities are absurd, right? We haven't even, the possibilities are so numerous, we haven't even thought of like a tiny fraction of all the ones that are probably there yet. And the reality model will be similarly incredibly powerful.
Yeah, and it doesn't always have to be done just with video. It could also be done within simulation.
Yeah.
One of the advantages of simulation is you don't have to label anything, because it already comes pre-labeled. But as far as the vision system would be concerned, it seems like it's seeing a video, and then you can go through all the different nuances and iterations you need to do, as well as the fact that they're also training with a live human, with the sensei going around moving that, actually using the sensor suite from Optimus already, which I thought was rather interesting. Did you notice that, James, that the helmet that he was wearing was not some special VR helmet, but it's something they actually took right out of Optimus and just plopped it right on there?
I didn't notice that.
Someone pointed out in a thread, because we were trying to speculate what was that, and there's this big backpack. Yeah, it's like, why does he need a big backpack for doing that? And someone thought, well, maybe that's actually the torso back there. So you get the FSD controller in the back, and then on the bicycle helmet, he basically is wearing what are now the 6 cameras that we believe are in the head of Optimus. So there's 2 to the side. There's 2 your normal ones, and it looks like there's 2 that are going down.
And so he needs batteries and a computer for gathering all the data, recording it to hard drives, and powering everything.
Yeah,
makes sense. So he can just, it actually, getting back to the human body as a model, most of the data that goes into our brain isn't vision. Most of it is from all the touch sensors and temperature sensors and proprioceptive feedback from our body. And similarly, factories and reality models, you can do the reality model just based on vision, but to really get, an entity like a robot in the real world, you want all that proprioception. You want it predicting that stuff too. So when it puts its foot down, if it's standing on sand, it notices from the feel of how, the sound it made, the vibration that came through. Like when if you're walking along, you suddenly step on some sand, you're like, danger, I could slip on this. And you know it without looking at it, right? You know it because of how it feels. And that's something that the robot and all the robots inside the factory working as a whole, like at the end of this thing, it has all those things, right?
Yeah, Hans, that thunderclap was me. So there's a big thunderstorm rolling through here. So don't be surprised if suddenly you hear a big bang or something like that, or suddenly I disappear. So that is going on. So James, I guess the other thing is that you were talking about walking on sand. I mean, it looks like Optimus can literally walk on eggshells now.
Oh yeah.
So when they someone mentioned that yesterday, like, oh yeah, actually it is walking on eggshells. It's able to do that. Yeah. So what did you think of that torque control system and how rapidly it's able to respond?
I'd like to know. I'd be more impressed if I understood the algorithm that they were doing under it, because there's some things, from doing factory automation, like those factory robots, they can do amazing things, mostly because of how fast their feedback mechanisms are and all that kind of stuff. If they were doing that with a neural network, well, that's actually pretty cool. That's a pretty, if that's a neural network control system that they're using for it, that's a pretty, and the thing that's impressive about it is not that it doesn't crush the egg, it's that it's adaptable. You know how, and that was, I think that's what they were trying to demonstrate. Like, look, we can keep changing the circumstances for this actuator to go down and apply pressure. And it's precise enough that when we slide an egg in there, and that's why the guy breaks the egg at the end, so that, like that, it's not a hard boiled egg. Like, this was a real honest to God egg.
Yeah. And when I looked at it, I said, it's not about the leg, it's about the hands, because if they get that kind of control system, imagine what that means for proprioception. So they would say, I'm closing the fingers down, and now this feels a little bit squishy, a little bit funny. They'd be able to tell exactly. And there was one item that they picked up, which was kind of a squishy item that was designed to do that it knew, oh, I need to apply this amount of pressure to figure out what the grasping force needs to be, not to break it, but also to make sure there's enough. It's not going to slip out of my hand when I try to lift it up.
Yeah, but you're right. That's a proprioception demo. We didn't say that explicitly, but just to make
that's the connection I made when I saw that, and I was wondering if anyone else had picked up on that.
Yeah.
So what's the significance of doing that in a neural net versus just having some basically having boundaries that are hard coded on safety, to where you have just like a little snippet of code that's more of an if then else type snippet of code that can control the or at least respond in an area where you've got something where maybe safety's involved, as sort of the guardrails on something that is an overall neural net architecture.
Okay, so your question, if I can rephrase it, is like, why is it impressive to do this with a neural network as opposed to a heuristic? Because we could also do this with the heuristic. Is that right?
Yes, but not necessarily. Like, instead of a stack of heuristics, having the control flow being through neural nets with some heuristics kind of bolted on the side to constrain the overall.
So the interface between neural networks and heuristics is always going to be a little bit wonky. If you can get everything into the neural network, you're going to have like less weird behavior. If you, you've got some behavior in some envelope you want the system to act inside of. And so you train a neural network and it generally stays inside the envelope, and maybe it violates the envelope slightly under, complex circumstances. The great thing about neural networks is you don't have to have 5 variables you define your thing in front of. You can have 1,000, you can have 10,000 variables. Like, it can take all that stuff in, integrate it, and figure out not extract the intent, but be able to responds to a much more complicated and dynamic situation than if a human has to decompose something into a set of heuristics. We typically, you get hard fail scenario type things. It doesn't fail gracefully, right? It doesn't adapt gracefully. Everything is, clunky, for lack of a better term. Now, if the problem that you want, it fits perfectly within your heuristics, you can do amazing things. The reason that we can fire a rocket and get to the moon, right, is because Newtonian mechanics it fits a simple heuristic incredibly well. And once you're a rocket in vacuum, like, your motion is pretty well defined by that. So we can do that kind of stuff. But like, if you want to like build a robot submarine and get to, swim to Japan or something like that, that's a much more complicated thing, because the environment you're dealing with is a lot more dynamic. You need a lot more feedback in that and that kind of stuff. So the neural network is much more likely to be able to pull off the fish swimming all the way to Japan thing, right? But the heuristic works really well if you're a rocket going through space, because, the motion and the environment are really simplified in that situation. In situations where we build a neural network, but we don't trust it, or where we build it and we want to integrate it with some heuristics, it gets complicated. It can get complicated, and you can get these kind of brittle boundaries. Like heuristics, they have this space of problems that they work really well on, and neural networks has a different space that it also works really well on. And when you start building the Frankenstein kind of stuff, now you have to be careful that you're not bringing in the weaknesses of both rather than the strengths of both. Like the interaction can get really complicated, but of course it depends on the neural network, depends on the problem, depends on the constraint you're trying to apply and that kind of stuff. As a general rule, if you got to put a guardrail on, you want to be the simplest possible guardrail with the widest possible boundaries so that the heuristics and the neural network rarely interact. You don't have to spend a lot of time planning for and testing the interface between those two. The guardrail only kicks in this very weird, rare situation where the neural network has just gone completely off the rails and you're trying to stop a catastrophe. Like if you can do that, then the heuristic's not such a big deal. But if you have lots of heuristics that are constantly tampering with the neural network, now, the world it was trained in isn't the world it's operating in. And now, the neural network also isn't giving you the best behavior. And we see a certain amount of this stuff. We've seen it with FSD and with AP over the years because they had neural networks and they had guardrails on them. And occasionally we would have these really poor behaviors that persisted for a really long time because the interaction between the guardrails and the neural networks was complicated enough that it was hard to fix without removing the safety that you're trying to have the guardrails bring to remove the certainty, say, the predictability that the guardrails are giving you. One of the weaknesses of neural networks is that they can be unpredictable. Like they do have this black boxy kind of character to them. They can be characterized. You can train a neural network. You can study what's going on inside it. You can characterize it and you can make them predictable, but it's a lot of work. It's a lot easier to just train the neural network and then use it in the real world. So, training a neural network, using it in the world and putting the just in case guardrails on, do not turn the wheel 90 degrees when you're driving 70 miles an hour on the highway. Like that was a guardrail they had for a really long time. And it was, it's an important safety thing because at the time that they had that guardrail, that was a thing that occasionally the AP would try to do. It's really, really stupid. And so that guardrail was, but then when the guardrails were constantly activating because they were getting used in situations, and that's when you need them, of course, right? If the neural network's making that mistake a lot and you can't afford to make that mistake, well, now you have a guardrail. The guardrail prevents it from making the mistake, but now you've got this very complicated behavior where, like, when does a neural network hit the guardrails? What does it think's happening when it hits the guardrails? How does it respond to hitting the guardrails? Because it's not necessarily trained in an environment where it's got the guardrails, right? The training environment doesn't have it doing the bad things that happen in reality. Anyway, it's complicated, but you can simplify it by having a competent model.
Yeah. I think the other thing is that it comes down to brittleness. And when you have something extremely complex, would you put your faith into some people writing the heuristics that are not going to fail, or a neural network that's been highly trained and might make really good decisions? And so sometimes my faith on how brittle heuristics are, especially when there's an interface, was demonstrated yesterday. My wife is filling out a form and suddenly it's just saying, the first name is invalid in the form. We're looking at it. Name is spelled right and everything else. It's like it's coming up red. It's like, it's not working. Why isn't it working? Then I figured, I was like, I know what happened. You probably had like autocomplete, because autocomplete just happens for you and it fills in the form. Well, what does autocomplete like doing? Well, it's like I'm trying to put words in a sentence and that a word's going to come after this word. So I always have to throw a space at the end of the word that I just put in there. Yeah. So I guess it's like, I bet there's a blank space at the end of her name. Sure enough, it was right there. And this just shows like two sets of brittleness. First, the autocomplete should not be so stupid as to always be inserting these characters you can't see that's going to arise in that situation. And second, the validation code in there, haven't they ever heard of string.strip? I mean, it's like the first thing you do when you get a string is you strip it to get rid of any hidden characters in the beginning of the end. Now, if there's a blank in the middle, you can get upset about that. And so again, it just shows it's not thought through. And that's how the API and everything is set up. And so
it gets complicated.
At some point, I don't trust heuristics. Something as simple as that, as filling out a form correctly. Still, here's 2023. How long has HTML been around? How long have we been filling these forms? And you still run into these problems.
But everybody makes those mistakes, right? And a mistake that's invisible is hard to catch, if it doesn't manifest. It isn't until somebody with some particular autocomplete on some particular thing and that your HTML, your script breaks,
It's the interface between the two, because no one was using autocomplete. So everything was okay. And it was really rare that someone was putting in the blank at the end. And then you were penalizing them for like, what are you hitting the space bar for? But even then, sometimes people will put the tab, and sometimes the tab will either go to the next form or it actually will insert a tab in there and you're not even aware of that. And that's screwing everything up. So heuristics are extremely brittle. And so sometimes, I almost think the neural net would have been a lot smarter understanding that. It would have looked at that and said, oh, yeah, name looks valid, and wouldn't have had a problem with it.
Yeah, maybe. But then what would have happened is the neural network would have passed on it. It would have gone into a SQL database where there's a space. There's now a space at the end of your name, and anybody in the future who tries to reference you without putting a space here into your name, like the SQL table's not going to
this won't work. Exactly. Which is just as well, because all the people trying to reference our name are spammers anyways.
Okay, I think we're about out of time. Do you want to have a topic you want to wrap up on?
That's really I've got, 100 more questions I could ask each of you, and y'all are very welcome to come back at any point that you're interested in talking with me. But yeah, I think that might actually be a good place from my perspective, unless there's something that either of you would like to wrap up on.
Scott?
No, I'm just thinking at some point, I've got a spreadsheet, but we don't have time for it now, to go through with you, just to get an estimate of how much we think it's going to cost to actually build Optimus. Because I know we've kind of pulled some numbers from out of the air to say, well, it should be right around here. And I've tried to go in there and be a bit more scientific about it to get an idea of a breakdown of the bill of materials. But I've got some wild guesses here and there on how much something would cost.
I mean, I'm much more interested in like how cheap could you make an Optimus, like a humanoid robot, like, given the constraints that, like the strength, the period of time that it can operate on a charge, the flexibility and all that kind of stuff. Like I'm very interested in, like, I feel like the world is different if this is a $50,000 robot than if it's a $10,000 robot. And if it's a $1,000 robot, that's even something different. Now, at that point, you start optimizing for, maybe we can make it a little more expensive, but make it so that robots can make the robots.
Right.
Yeah. So I'm being curious to see like what you have in there now and where you think it could go.
So you have like another 5 minutes?
No.
Oh, okay. All right.
I'm running out of time. And it wouldn't be 5 minutes. Like that's
we'll be 5 minutes. Okay.
I'm happy to host that discussion, or if y'all would prefer, I know that you both like to have hosts, so either mine or if you want to do Dr. Know-It-All's channel, just let me know.
Yeah, cool. Yeah, sure.
Yeah,
sure.
That'd be a good one.
Yeah. As you know, both James and I we're YouTube squatters. We don't have our own channel.
Hey,
so
we're happy to have
how's
you.
Dave Lee's couch? Is it pretty comfortable there, Dave? James?
Yeah, it's
No, I'm imagining that you sleep on Dave Lee's couch a lot. And,
I sleep on his.
No, I'm sleeping on John Gibbs a lot because we're just squatters, we're just like wherever you get brought in.
Okay, on that note, I'm going to take my leave.
All right.
Anyway, thanks for hosting this, Hans. It was a fun discussion. I had I enjoyed it very much.
You're welcome, and thanks again for hanging out with me. We could talk for hours. So, all right, everyone, we will see you in the next one, and we'll definitely let you know when that's going to be. So look out for, you can, if you follow me on Twitter, that's where I post the links to videos in advance. And then follow both James and Scott are on Twitter, and their Twitter handles, if you're not on Twitter, their Twitter handle should be in the video description of this video. So, all right, everyone, have a great day. Thanks. Bye.